Well, hello. Welcome to the MCube Weekly Seminar. Today our speaker is Austin Harris. Austin has been an ASP postdoc now since July, but you may have seen him lurking in the hallways for for some time. Because he came here as a graduate student visitor in 2021, never left. So there he is. And don't let him tailgate you inside the. Or you can let him. You're not supposed to let anybody tailgate you, right? Even if it's your mother, you can't. No. All right. All right. Austin has a PhD and an MS from University of Wisconsin, Milwaukee, and a BS from the University of Oklahoma. Contrary to his current physical appearance, he's not a fan of NASCAR, and does appreciate a good Miller Lite. Austin.
Thanks, Rich. I hope to make mullets proud here during this presentation. So many of you have seen teasers of this talk over the last couple of weeks and months, but glad to share the full thing here. It's really a culmination or an overview of my PhD work and also the work that I very much plan on doing for the next couple of years here at NCAR. Also kind of make a case for agent-based modeling being here to stay longer term at NCAR. But first, I'd like to acknowledge my collaborators, Rebecca Morse, Chris Davis here at NCAR, and also Paul Rober at the University of Wisconsin-Milwaukee. Without their support, this wouldn't be happening, and I'm very, very grateful. And there's many more people here in this room as well who have supported me throughout this process too, so thank you. Before getting into the research, I thought I'd provide a little background on myself. I'm very much one of those meteorologists who can trace his interest in the field back to a specific point in time. For me, that's May 3rd, 1999, in Moore, Oklahoma. That F5 tornado rolled to the town, missed my family, friends, everything. Everyone was fine, but we were less than a mile north of that particular tornado, which put us in the forward flank downdraft after the storm, which is why I'm seen there at the age of 8 holding these big hailstones and quite excited about it. That particular moment left a very lasting impression on me. I wrote shortly thereafter that I planned to go to the OU School of Meteorology. I was going to work as a storm chaser, and eventually I was going to work in the severe storms lab issuing warnings. And in my later years, because I had it all figured out back then, I was going to work as a newscaster meteorologist, so we'll see. I did do some of those things. So I went to OU for my undergraduate degree, had a short stint at the University of Reading with a study abroad program there in England. It was a lot of fun, didn't do much studying. 2014, I made it to the University of Wisconsin-Milwaukee for my graduate work. I did take an unexpected gap year in between there. At the tail end of my senior year, I applied to a bunch of graduate programs, was rejected by every single one of them, and then reapplied a year later, got into one school, and it was UWM, and I'm so, so grateful that it worked out that way. At UWM, for research, I worked with Dr. John Call, who's a great mentor of mine, on wind gust forecasting techniques, and I still dabble in this area today. If you're ever interested in talking about it, let me know. The other thing I did up there that was very impactful was work for a forecasting group called Innovative Weather. So this particular group, we forecasted for a variety of clients in the upper Midwest, including the Milwaukee Brewers, which was a lot of fun, and the local NPR station as well. We did radio interviews for them, a bunch of power companies, and we'd be on the phone with them. So it was a very good experience for me, and it took me down the operational path for a while. I went to the Weather Service in their Warning Decision Training Division down in Norman, Oklahoma. We provided training for forecasters both online and in person. The in-person component was a lot of fun because we brought the forecasters first, second years in and ran them through these simulations where they could practice issuing tornado warnings and severe thunderstorm warnings, flash floods, and then we provided feedback to them. So it was a cool experience. Eventually, I came back to research, though. So Dr. Paul Rober reached out to me in 2018 to see if I was interested in working on a project, and I very much was. Thought it would be a good opportunity, so I came back to Wisconsin to work with him. Before I worked on this agent-based modeling work, which I'll talk about here, I did spend a little bit of time working on the NBA home advantage phenomenon, modeling it using artificial neural networks, which was pretty cool. And coincidentally, during that particular time when the study came out, the Milwaukee Bucks were doing really good. And so the local media were like reaching out, asking questions about it. It's funny how that works. So that's where that picture came from. But yeah, so eventually started working on this agent-based model work. And one of our first courses of action, Paul and I, was to reach out to Rebecca Morse to see if she was interested. Fortunately for us, she was. She was enormously helpful, as you'll see throughout this particular project. But it also gave me an opportunity to come here. In late 2021, came here as a graduate visitor, and as Rich alluded to, I hadn't left, really, except for a short one-week period where I did drive back to Milwaukee to grab my things, and then returned back here. So very attached to in-car and Boulder generally. I finished my PhD up out here, which is why I was lingering in the hallways, and I stayed on as a postdoc temporarily. And now I'm here as an ASP postdoc for the next couple of years. So, oh, and Austin and I got a dog last week, which is, so I couldn't help but share the photo down there of Boo. Thank you. So on to the agent-based modeling work. The origins of this project, at least in Paul and I's minds, really came from watching Hurricane Irma evolve in 2017. It started out like, I guess, most hurricanes do in the Atlantic, kind of progressing westward. Then at some point, it became really clear that it was going to be a very impactful storm, including for the Florida Peninsula. At this point, I think the Florida risk was starting to increase. Then over the next couple of days, as it impacted the Caribbean islands, it made its way towards Florida, and the first evacuation orders for the mainland US started being issued. First around the Florida Keys, and then eventually towards the Miami region. And those evacuation orders over the next couple of days spread up and along both coastlines. And so basically the entire Florida Peninsula coastline had evacuation orders. Over the next couple of days, as the forecast information evolved and became more certain, it became pretty obvious it was going to impact South and West Florida and the Florida Keys. It made a landfall in Southwest Florida there. First in the Keys and then a second one south of Tampa Bay near Fort Myers. But throughout this period, there was a slight westward jog in the forecast track, very significant westward jog. But it was a very impactful storm. Just looking at the evacuation itself, over 7 million people evacuated for this particular case based on those forecasts. It was the largest evacuation in US history. As you might expect with an evacuation that size, there was a ton of traffic. Both I-95 and I-75 were very slow going for multiple days before landfall. And there were actually gas shortages during this particular event, which are quite notable and unique for some of these events, I would say. But for us, we noticed, obviously, the forecast and warning information itself is quite complex. It's dynamic. It changes over time. But also the human side of things, too, is quite complex. There are many different people making many different decisions, including emergency managers and households deciding when to evacuate, if to evacuate, where to go. There's also traffic engineers and traffic managers trying to make decisions about how they can best support the evacuation. One of those decision points was whether or not to implement contraflow during Irma. Contraflow is the process of taking both the inbound and the outbound lanes of major interstates and making them all outbound so you can get more people out safely. But they actually decided against implementing that here in this case because there were fuel shortages, and they wanted to make sure that fuel tankers could get back into the most impacted areas. Very complex, right? There were also some evidence, I would argue, in this particular case that these systems and interactions are quite nonlinear. With the traffic piece, there were quite a bit of reports of people deciding against evacuating for Irma because there was so much traffic. They just didn't want to deal with it. So in that particular instance, the amount of traffic was feeding back into human decision-making aspects, which of course affects traffic again too. So it's complicated and nonlinear. And then also, even though this, I would argue, was a very good forecast meteorologically speaking, based on small track errors and intensity errors, it was also a very challenging one with the particular angle of the storm coming up the coast the way that I did. There were examples of a few people, like say in the Miami area, who left pretty early on in this event, and they went upstate and they went inland. Some reports of them going towards Orlando and Tampa Bay, which at the end of the day probably received a greater impact from the storm than Miami did, arguably speaking. So it just kind of illustrates the complexities involved there too. So hurricane evacuations are complex. That was the point I'm trying to make here. So Paul and I started digging into the literature to see what we know about hurricane evacuations. And it becomes pretty clear right away that there's a lot of information out there, mainly through surveys and interviews of storms after the fact, after they roll through. Depending on how or what you count as being a study on hurricane evacuations, I would argue there's at least 75 studies out there on evacuation behaviors, if not many more, for over a dozen storms that have passed through and affected the mainland US. There's enough data out there that there's literature reviews summarizing a lot of this work. Most of it, I would argue, revolves around household decision-making during an evacuation here, including who evacuated, where they went, when they left, how they got there. And a lot of, and this is the reason I have this particular bit highlighted, a lot of the focus of the area work is to understand what motivated people to evacuate, why they made those decisions. So there's been a lot of work done there. There's a whole body of literature around forecast visualization and how people perceive risk based on those visualizations. There's studies on emergency manager decision-making. We generally know when and where evacuation orders were issued for an event. Andrea can attest that's actually kind of difficult to find that data, but it can be done and it's out there. We generally understand people's emergency managers' motivation for the evacuation order decisions too. So, and in regards to traffic, we know the location and timing of traffic. There's cameras out there and counters and things like that. And we generally know what evacuation management strategies have been used or if they've been used at all. So there's a lot of work that's out there already. And there are new methodologies being developed to study evacuations even further. Social media analyses. Robert Presley is leading that work. Julie DeMuth is leading pre-storm surveys or surveys being implemented in the lead up to an event to monitor people's risk perceptions and how they're evolving over time. So there's new strategies being developed, and there's also cell phones that provide a very rich and complex data set out there that people are just now starting to dig into and figure out ways that we can use that data to study evacuations. It's a pretty new area of work, but I think has quite a long-term potential to develop and foster our understanding of hurricane evacuations. But of course, the human side of things is very complex. So even though there's a lot of data out there, much more is needed. So it's very much ongoing work, right? On the flip side, there are evacuation models that exist. They can be informed by, and they should be informed by, and validated against empirical data that is taken via the mechanisms and stuff discussed on the previous slide. But the benefits of models relative to empirical studies is that they can be used to explore completely hypothetical scenarios that haven't been studied yet, or just completely new ideas, new situations, and evaluate the evacuation response to them. One example of that is in this type of modeling framework, you can test out and implement evacuation management strategies, something that you don't have to implement in the real world to see what its effects would actually be. So when looking at evacuation models, I would argue that most of them are statistical in nature or differential equation-based type of models, particularly on the traffic side of things. A lot of these models start with some kind of statistical estimation of what evacuation rates would look like for a particular storm and scenario, and that data gets ingested into a traffic model, typically a differential equation-based type of traffic model that models traffic much like fluid flowing through a pipe, using those differential equations that I don't fully understand myself, but there's quite a bit of models out there that do this particular stuff. They're run quite quickly, they're typically quite fast, and the reason for this is because they tend to support decisions made by emergency managers, traffic engineers, and officials, so deciding whether or not to implement certain strategies beforehand. On the flip side, there are some agent-based models of evacuation that are out there. They're less in number, I would argue, than the statistical and differential equation-based type of models. They can be slow depending on the amount of stuff that you put in it. My particular model is quite slow. But they tend to be focused on knowledge building. That's, I would argue, their advantage relative to these more decision support type tools. What is an agent-based model? It's a type of computational model for simulating the actions and interactions of autonomous agents in order to understand the behavior of a system and what governs its outcomes. Just rip this from Wikipedia. They are a kind of microscale model where higher level system properties can emerge from the interactions of lower level subsystems, or macro scale state changes emerge from microscale agent behaviors. So it's this relationship between modeling the microscale and seeing the emergent behaviors that come out of those interactions. They're used in many scientific domains, including biology, ecology, and social sciences. I would argue their roots are more in ecology and computer science. You don't see them, as you might expect, in meteorology too much, but there are a few for hurricane evacuations. So Paul and I, we started looking into agent-based models. He had already done a study using agent-based models before. Rich.
Yeah, so could you define autonomous agents?
Right, so as you'll see in this particular use of an agent-based model for hurricane evacuations, an autonomous agent might be a household making an evacuation decision, which is unique and autonomous from the other households also making decisions, but they can interact. Exactly.
What's a non-autonomous?
That's a good question. I think they're just autonomous in the sense that they are their own entity and can govern their own outcome generally. But one key feature of agent-based models is that you allow those agents to interact with one another in order to get this kind of emergent phenomenon beyond. So, yeah, we looked at agent-based models and some of this description, and we basically came to the conclusion that it seemed like it would be a good fit for evacuations in particular. So we progressed forward. We looked in the literature, found a few agent-based models that focus on risk communication, one of those being the CHIME model developed by Rebecca and many others, some in this room, and also agent-based models of decision-making during evacuation as well. There's a small separate body of literature using agent-based models to model traffic. But what you tend to not see are agent-based models that model all of those components together, the risk communication piece, the decision-making piece, and the traffic flows. So there was a gap in the literature there, and we think that those components very much interact with one another, so it seemed reasonable to try to make a modeling framework that does those things. Another thing that we saw with the literature that exists was they tend to oversimplify, arguably, the meteorology side of things and have the forecasts either be static or, just not as complex as it really is in the real world. So one thing we try to do with our modeling framework is make some quasi-realistic dynamic representations of the forecast information and see how a lot of that information will propagate through a model system. So for about 2 years of my life, I built this model here that we call FLEE, the Forecasting Laboratory for Exploring the Evacuation-system. Now, FLEE includes the representation of the natural hazard. Of course, here it's the hurricane, and this quasi-realistic dynamic representation of its hazards in the forecast there. And you can do this for both real and hypothetical scenarios, and I'll show some examples of both. We model the human decision-making aspects. That includes decision-making by emergency managers, but also households making decisions as well, and the flow of information too. And then there's the built environment piece, a road network where agents can evacuate along a model grid. So we model those components together and different connections between systems too. The idea being we have a model framework that links all these components together where we can then explore the system's dynamics, how these components interact with one another and where the nonlinear feedbacks exist and so on and so forth. And as a meteorologist, I'm particularly interested in how that forecast information and the uncertainty associated with it propagates into the other systems and generates an evacuation outcome. So that was the idea behind this modeling framework. And as a starting point, we made it very idealized, as you'll see. So the idea was not to represent every feature imaginable that could be known or attributed to an evacuation, right? It was just more of what are the key features, let's model that, start from there, and then see where it takes us. What can we learn? So the modeling framework has been described in painstaking detail in this particular journal article right here. So I will, over the next couple slides anyways, provide an overview of the modeling framework, but a lot of the details I will note are there. So the model. The forecast information in FLEE really, the way we've designed it, starts out with Hurricane Center archived forecasts, like say from Irma shown here. It doesn't have to be archived Hurricane Center forecast products in theory. It can be a lot of different things, but this is the starting point for us. And we overlaid that forecast products onto an agent-based model grid. In this case, it's a 40 grid cells, basically, where agents are located and they're making evacuation decisions. But the forecast information, it's overlaid onto the grid, and then for each of those grid cells, we combine the levels of risk to produce a hazard threat score represented as a red, orange, yellow, green representation of risk. That's the magnitude of risk expressed there. It's a very simple way of doing it, and there could be many other ways of doing it, but the idea there was to combine and synthesize the forecasts information, much like how broadcast meteorologists would simplify and communicate the information to the public and give a specific location-based type forecast for a lot of folks. It's also a very practical way for us to connect the forecast products with our agent-based modeling grid, where evacuation decisions are being made. You can also create hypothetical scenarios, which I will show in the next couple of slides. But theoretically, you could attach some model data to this type of modeling framework, right? You could attach ensembles or deterministic forecasts if you'd like. I haven't figured out a way quite yet, but theoretically, this absolutely can be done. Emergency managers are located within each of those grid cells, and they get to decide if and when to issue an evacuation order. Now, we have them issuing evacuation orders if there's any kind of surge threat. So it kind of limits the evacuation orders to the coastline. And we have them issue the evacuation orders when the estimated arrival time of tropical storm force winds equals a grid cell's clearance times, which in emergency management, there are many studies out there that estimate the amount of time it takes to evacuate certain areas. So emergency managers know this ahead of time and know generally how long they have before issuing an evacuation order. So that information is combined, and then these emergency managers issue these agents. In the case of Irma, based on that forecast information shown there on the left, the simulated emergency manager agents in FLEE first issue evacuation orders in the Miami area, and then those spread up and along both coastlines, eventually encompassing the entire Florida coast. So that does match what was observed or what we had seen with Hurricane Irma. So that's good that this component of the model framework is in the ballpark. Now, there are many households on this Florida-like agent-based modeling grid. There are over 4 million households, in fact, and they're making decisions on whether or not to evacuate. We have them start that decision by taking in forecast information, some representation of risk of the wind surge and rain hazard, rain threat for their particular grid cell. They have information on whether or not they're under an evacuation order. And they also have some household characteristics, like whether or not they live in a mobile home or the average age of their household. The idea being these are the most common or widely known factors to influence evacuation as seen through the empirical literature. Of course, there are many more than this depending on the case, but there's a lot of variety between cases. So we thought this would be a good starting point in terms of information that gets ingested into this part of the model. But those factors are combined to generate a household risk assessment, which these factors are weighted differently from household to households. And the difference in weights is really meant to provide some kind of representation of the complexities of these decision-making and to also simulate all the other factors that might be involved in the evacuation decision-making process as well. So it's such that like you and your neighbor can have the same forecast information and information on evacuation orders and even the same household characteristics, and you can still come out with a slightly different risk assessment. But ultimately, that risk assessment is then compared to any evacuation barriers that might be in place, such as whether or not you have a car, whether or not you have the money to evacuate, and also whether or not you actually can based on the amount of traffic in your area. And so in that sense, there's some nonlinear feedbacks within this particular system as we've designed it. At the end of the day, you decide to evacuate if your household risk assessment is greater than the evacuation barriers that might be in place. And if you decide not to evacuate, you come back to the decision in about 30 minutes and reevaluate again. So that's how that part of the modeling framework works. Households are geographically distributed in such a way to represent the actual population of Florida. So that's where the spinny stars there were meant to indicate Jacksonville, Orlando, Tampa Bay, Miami as well. So agents are distributed in a semi-realistic way. Then we have road networks that we've overlaid on top. So there are many two-lane highways shown there in red that allow agents in the middle part of the grid to pack up and move to the outer parts of the grid where they can hop on some major interstates that have 5 lanes associated with them, shown there in blue, that allow agents to flee northward and off the grid if they like. Those roads are like I-75 and I-95 in Florida. That's what they're meant to simulate. Then there's some east-west running interstates as well, shown there in purple. And they help allow agents, say, in the Miami area to go up towards Orlando if they like, or Tampa Bay even. But the main point is that based on this type of model, we allow the agents to actually move. They can move between grid cells, they can move off the grid. Their destination, that information is taken from surveys, particularly for Hurricane Irma, which showed that over half of the evacuees actually left the state entirely. The other half went upstate, they went inland. So we try to emulate that here in the modeling framework too. You can also adjust the amount of lanes of traffic as well, and that's something we'll do in a later slide, but that is a piece we absolutely have control over and is interesting. And I added this here, which is a very localized snapshot of what the evacuation traffic looks like in the model over a 4-kilometer, shown there on the y-axis, stretch of road over, say, like 5 minutes. You can actually track these cars as they progress down along a piece of road. Each of those dots, the dots shown in red, are vehicles that are moving at full speed, and then if they turn blue, it's because they've slowed down. You could do this an infinite number of times. I don't want you to get hung up on it. I just wanted to illustrate that at the microscale level, there's absolutely a lot happening with respect to the traffic piece of things. But we, of course, are much more concerned about the larger level patterns of traffic. So I've highlighted here kind of the key outputs, so the things that we're really looking for in this type of modeling framework. One of them being evacuation decisions. And I've shown there the percent of households in a grid cell that's successfully evacuated. So they're like evacuation rates. You can look at the evacuation rates in a number of ways to determine a successful evacuation or not, but I've highlighted the grid cells that are under evacuation orders in red, and the grid cells that experienced hurricane force winds, kind of arbitrary, but experienced some level of impact with the storm with the dotted cells. So you can see that the highest evacuation rates for this Irma case here, based on the forecast information that's kind of grayed out there on the left now, the highest evacuation rates are in Southwest Florida, which is kind of what you would expect. And there are less evacuation rates upstate and inland. But overall, a lot of people evacuated all across the model grid, which is consistent with what we saw with Irma. So that's one way of looking at the model output here. Another one is to say, look at the percentage of households that gave up evacuating due to traffic. Like there was so much traffic in their area that it dissuaded them from evacuating in the first place. With Irma, based on these forecasts, we see it's mainly around Tampa Bay. It's on the west side of the model grid and the south as well, where you had higher numbers of people deciding against evacuating because there was so much traffic in their area. So it provides a sense of, in the macro scale, where the traffic really was affecting evacuation outcomes. Okay, I think this might be a good stopping place for questions before I get into some analysis using the model, if you feel inclined. I also don't like talking for more than 20 or 30 minutes without a break.
Yeah, questions or comments or points of clarification? Or? No, I guess not.
Gonna make me talk.
You could take a break. You could take a break anyway.
Okay. Water.
Ah.
Hey, this may be something you're going to get into the next part of the talk, but I was curious. So this is integrated through all the NHC forecasts for Irma, what you were showing. How I guess some of the dynamic questions is, how soon were people evacuating in your model versus either real life or like kind of what lead time did most of the factors in your model say for most people, hey, go evacuate?
Yeah, that's a great question. For Irma, it was pretty early. And that matches, there is empirical data that tracked the evacuation timeline temporally. It was fairly linear, starting like 5-6 days in advance, and it just kept on going and kept on going. I do have a slide that I can show at the end, I think, that tracks the evacuation rates over time. But yeah, it happened pretty early on.
One other question, I guess with the differences between east and west coast of Florida, how much of that is due to forecast versus the different like kind of demographic compositions of the east and west coast of Florida, where like west coast of Florida has a lot more retirement communities and like fewer bigger cities and more like residential kind of stuff?
Yeah, that absolutely is a big component. So there's that piece too, and a very large and important factor too are the amount of mobile homes in areas. Within Florida, the central part of the state and upstate, you have as much as like 40 or 50% of, in our case, grid cells, but depending on how you break it down, zip codes, whatever, are mobile homes. And mobile home ownership is a big driver for evacuation as well. So yeah, that was a very big part of the modeling framework and a very big determining factor for some of these outcomes. I think it's one of the reasons why you end up having evacuation rates be as high as they are in north central Florida up in here. A lot of the reason for that is mobile home ownership. Great question.
Interesting.
Cool. All right, so in this part, figured we'd actually do some stuff with the model. And I will note that this is its publication in the Natural Hazards Review. One of the first things we really do in this particular part of the paper is explore how FLEE and its simulated evacuations compare with observations, particularly for Hurricane Irma, but also to some degree Hurricane Dorian, which I'll show in a second. And we look at whether or not our evacuation orders match, whether or not the evacuation rates, the spatial and temporal pattern of them are matching the empirical data. And same goes for traffic, is high amounts of traffic in our model occurring in the same place as they are in the real world. And then a third hypothetical scenario that we look at here is what we call a rapid onset version of Irma. Basically what we do is we take Irma's timeline and we speed it up. The idea being to try to simulate what it would be like to have less time to evacuate, or that the storm scenario is just a little bit more unexpected, giving you less time to respond. So I'll show that later on. But for each of those scenarios, we also look at public transportation and carpooling. We implement that in our model framework by changing the number of people evacuating per car, which changes the amount of cars on the road. We add what we call contraflow, which is the process of adding additional lanes into the model grid. And we shift around the evacuation order timing. We also increase the population to what it would be projected moving forward in 2030 and 2040, and see how that affects evacuations. But when implementing all these different changes, we're trying to see how they compare with one another in terms of the evacuation outcome, and also how they vary across forecast scenarios, and which regions in the model are most impacted. The first scenario, Irma, which we've talked about already, where the majority of the model grid was under threat throughout the event. So a lot of people evacuated for Irma. There's also Hurricane Dorian in 2019. And if you can recall, the early forecast for Dorian called for a pretty impactful storm along Florida's east coast. What ended up happening was the storm slowed out and stalled out over the Bahamas, devastating impacts there. And when it reaccelerated northward, narrowly missing Florida's east coast. So it was a close call, but there were evacuations on Florida's east coast, which we try to simulate here. Then there's that rapid onset version of Irma that I mentioned earlier. Basically, we take Irma's forecast timeline and we speed it up. We kind of condense the timeline down in such a way that it simulates what it would be like to catch people off guard a little bit. These are the same evacuation rates that I showed in a previous slide on the top panel, and in the bottom panel are the percentage of people who ended up giving up evacuating due to traffic. So the bottom panel shows the amount of traffic in a certain area, basically. The evacuation rates and traffic are pretty similar to observations. I have a slide later on that I can show you that details each of the validation components we could talk about. Dorian, this was an interesting case. In our model, the evacuation orders were issued basically along the entire east coast of Florida, which is what we ended up seeing with Dorian, with the exception being the Miami metropolitan area. It started just north of there. And in terms of evacuation rates, they were highest where you would expect them to be, which is along Florida's east coast and up towards Jacksonville, with relatively few evacuations further inland. Again, that matches what we ended up seeing with what data does exist for Hurricane Dorian's evacuation. Then there's the rapid onset version of Irma, which is overall quite similar to the outcome we had when simulating Irma's events. The main difference being in the bottom panel there, that there was considerably more traffic during this rapid onset type of events, which is something that I think makes sense conceptually, right? With people having less time to evacuate, they can get stuck on the roads more easily, and having a less than ideal sort of outcome under that scenario. So there's some evidence in this case that these rapidly intensifying or rapid onset type storms could actually worsen evacuations. Again, that makes sense conceptually, but it's the first time in a model that we're actually capturing some of these interactions, which I think is pretty interesting. For each of those cases, we implemented contraflow, just adding additional lanes of traffic on I-95, I-75, all across the model grid. Then we can look at the evacuation rates as a result. With Irma, we ended up seeing slight improvements in evacuation rates, and this is evacuation rates when averaged across the entire model grid. So these changes seem quite small, but actually these are over 100,000 more people that are able to actually evacuate for an event. And you see a reduction in the number of people who are giving up evacuating due to traffic. It's not unsurprising, I would say, right? Contraflow works. That's what this is basically showing, and it shows that the model is kind of doing what we would expect it to, which is good. You see less improvements in Dorian, but there was also less traffic in Dorian, so it was less of an issue. In the rapid onset version of Irma, where there was a ton of traffic, contraflow was especially helpful. Makes sense. And if you look at the improvements in evacuation broken down by grid cell, you'll see that it's the highly trafficked parts of Florida and Southwest Florida that have the best improvements due to contraflow. We did some experiments involving public transportation and carpooling. Basically what we did there was we took our default 4 people per car, and then we made it such that only 2 people would ride in a car. And then we also had these kind of clown car scenarios where we packed 8 people into a car, which changed the number of cars that were on roads for certain evacuations. We saw that when going from 4 people in a car to 2, which effectively doubled the number of cars on the road, you end up seeing the evacuation rates plummet because there was just so much traffic that people were giving up a lot more than they were originally. So you saw similar results with Dorian, and again, especially with the rapid onset case, where there was already a ton of traffic to begin with. Fewer cars, the better. There's the population growth experiments, which I thought were pretty interesting, where we went from 16 million people being on the model grid to projecting it forward to 19 million and also 22 million people. And we saw evacuation rates start to drop. With more people on this modeling framework, it just becomes more difficult to get everyone out. As you would expect, evacuation traffic increases in this. You get the same results again for Dorian, also the rapidly intensifying or rapid onset version of Irma there. So population growth could be something to look out for moving forward. You know, it may be that we need to implement contraflow more frequently during these type of events or take some other kind of protective action. I just think it's cool that this sort of stuff is in a modeling framework. So some things that we were able to use the model for, we showed that rapid onset, or we've provided a little bit of evidence, I would argue, that rapid onset may actually be worsening evacuations moving forward. Again, that's something that makes sense conceptually, but it's cool that it's in the model. We were able to implement public transportation and contraflow and show that it improves evacuation outcomes in our model, which is what we would expect. That's good. And then we showed population growth may be something to look out for moving forward. So, in addition to this, we're able to pinpoint exact areas where contraflow and public transportation would be very helpful. We can target certain areas and certain events that this sort of stuff may be most essential for. So really, I think my takeaway for this particular section is that agent-based modeling frameworks like FLEE, they can be useful tools for studying evacuations across many scenarios, both real and synthetic, with the synthetic part being kind of powerful in its own right that you can't do empirically. So for this bit, just quickly honing in on being able to explore the impact of forecast errors of evacuations. We also looked, so what I'll show you here are experiments adjusting the amount of certainty associated with the forecast track, but we've also looked at shifting around forecast intensity and seeing how it affects evacuations. Just wanted to throw that out there as something that we could talk about later if you like, but the main experiments we did were, in this case for Hurricane Irma, we took the best track, made a forecast out of it using the cone of uncertainty in 2007. So this is a pretty wide cone because the cone of uncertainty is representative of climatologically the amount of forecast errors associated with a certain period of time. So in 2007, the cones were much bigger than they are today. Then we compared this forecast with the best track forecast for Irma, but using a more narrow cone representative of forecast errors in 2022. So it's a smaller cone. Being able to compare the two allows us to kind of get at this particular question here, which is, are improvements in track accuracy over this 15-year time period actually translating to any improvements in evacuation? So that's the goal that we were working towards with these experiments. And what we ended up seeing was a slight reduction in false alarms between the two cases with different size cones. So on the left are the evacuation rates for Irma's best track forecast with a 2007 cone, on the right with a 2022 cone. And to make it easier to see the difference between the two, the difference plot is shown right there on the right. What you end up seeing is that along the easternmost part of the grid, which is an area that you could argue is less impacted than the south and west part of the model grid of Florida, you see a reduction in evacuation rates with a smaller forecast cone. So to us, that means you can make the argument anyways that this is a reduction in false alarms for those particular areas. And you ended up seeing less traffic in these particular areas as well. So depending on how you look at it, you could view this as an improvement in the evacuation outcome, depending on how you look at it. We more or less repeated these set of experiments, but with a hypothetical version of Dorian, where it actually makes landfall in eastern Florida. The way I went about creating this particular case is I took the archived Hurricane Center products for Dorian, including the storm track, and I shifted it west 70 kilometers, such that the storm actually impacts Florida's east coast in this hypothetical scenario. And on top of those forecasts, I overlaid the very wide cone representative of errors in 2007, and I compared them with the same forecast scenario, but with the smaller cone of 2022. And you more or less see the same kind of outcome, where here are evacuation rates shown for the 2007 cone. Evacuation orders, again, are highlighted there in red. So all of Florida's east coast is under an evacuation order, with highest evacuation rates out east, but still some significant evacuations along the west part of the grid as the storm has been shifted further over to the west. But the smaller forecast cone, you see less evacuations out west. And here's the difference plot to emphasize the differences between the two cones. So the smaller cone was a reduction in, again, you could argue a reduction in false alarms because those areas in the model didn't experience hurricane force winds. They probably would have experienced some impacts from the storm, but depending on how you look at it, you could view this as some progress in terms of the evacuation outcome based on this difference in the amount of uncertainty between the cases. Through this particular part of the modeling framework, we were just trying to make some small steps towards demonstrating how agent-based models could be used to explore this relationship between forecasts and forecast uncertainty with evacuation outcomes. Take a couple steps towards that direction there. So in conclusion, to summarize here and wrap all this up, I wanted to stop and talk a little bit about what my plans are over the next year, year and a half, open the floor, get some feedback from people too, if you're willing to share. Happy to talk to you afterwards as well. And then also to kind of make a case for agent-based models moving forward. So here's a table of what I am planning on doing over the next couple months, gonna stay busy, to create a new modeling framework or just to improve upon the existing one. I'll call this Fleet 2.0 until you can come up with a better name. The first order of business is to put the model framework onto a supercomputer here at NCAR. The reason being, it'll allow me to run many more simulations and experiments. Currently, this model of framework takes a long time to run on my laptop or a PC, about 3 to 4 days. So it's pretty slow, but getting it on a supercomputer would be especially helpful to get more simulations going. I'd like to improve the spatial resolution from where it is currently. When shifting around the forecast track, it's difficult to capture the evacuation response to very small changes in the forecast track because each grid cell is like 70 kilometers by 70 kilometers. So it's not able to capture small changes in that track. And in a similar way, I think it'd be helpful to change the amount of forecast risk categories from the very simple green, yellow, orange, red to something a little more colorful. That way we can better capture changes to the intensity forecast as well in terms of their evacuation response. Hurricane Ian provides an opportunity to explore another case and validate it against some real-world empirical data, which of course adds more confidence into this modeling framework. And as each of these evacuation scenarios unfold in the United States, it will probably provide more data for us to improve this modeling framework moving forward. There are many ways to evaluate evacuation success too, and so I think it would be interesting to add an economic component to the modeling framework or even power outages. Just some possibilities there. The big picture idea of what I'm trying to focus on moving forward is how hurricane forecast information propagates through the system and affects evacuation outcomes. And in particular, this research question here, which aspects of the forecast, whether that's the intensity aspects, forecast track, storm size, which of those are most important to accurately predict with respect to an evacuation outcome? And does it vary with different measures of evacuation success? Another type of question we could potentially explore here are there diminishing returns in forecast accuracy with respect to evacuation outcomes? And also, how do these answers vary in future built environments and population scenarios too? That's one of the beauties of this modeling framework, is that you can adjust those components as well. And then longer term, you could view this as a case for agent-based models in meteorology moving forward. They're gonna get better as the empirical data improves as well, and that's updated and ingested into the modeling framework. And as computing power increases, you can fit more and more into these models to run simulations. You could extend an agent-based modeling framework like this to other regions of the United States. We don't just have to hone in on Florida. There's many other places and locations where this could be especially helpful. And you could extend it to new phenomena as well. I think wildfires are a very interesting place where we could study wildfire evacuations and the connections between the evacuation and the built environment and the forecast itself. And these type of modeling frameworks, they take social science data, as I've shown, and combine it with physical aspects of meteorology and science, and basically they bridge the physical, social, and computational spaces as well. It's, in this way, you could view it as convergent research, and NCAR is one of those rare places where we do all of these things simultaneously in the same lab, and it makes this type of work a really great fit for a place like this. So with that, I will stop, answer questions, and really thank you so much for your time today. I appreciate it.
So I think we could start with the Slido question. Any thoughts on the Lahaina wildfires, very rapid events, and constrained evacuation routes?
Yeah, I don't know too much about how the wildfire happened. Others here might. To me, it seemed quite complex. And another example of interactions between the built environment, possibly climate change, weather conditions, and an evacuation too. I just think you could very much extend an agent-based modeling framework to explore these types of questions at some point down the line.
First of all, I apologize because I probably asked you this when you were in my office a few weeks ago, and I have completely forgotten the answer, so I will ask again. So what are you using to determine the time of arrival of 34 knot winds? Are you computing that from data available in the best track, like the wind radii and the track, or are you using their product?
I was using their product from the Hurricane Center.
Are you using the most likely or worst case scenario? I can't remember which one you picked.
Ooh, that's a good question. I don't remember either. But
Okay.
most likely.
Anyways, we can talk about that.
Yeah.
I just wanted to put it out there as an experiment idea. I know I mentioned it before, but I will mention it again, is that there's a group of scientists working with NHC to make some improvements to the wind speed probabilities that is going to drastically change the time of arrival estimates that NHC produces. And of course, they are really looking for ways to understand how this is going to impact users. And so that might be a test scenario that you might consider doing if you feel good about it with your model. So That was one suggestion. And I'm going to sneak in one more question if that's okay. So how are you validating this? I might have missed that, but I'm just curious, how do you know this is a good model?
Yeah, a great question and a very important one. Let's see if I can find the slide that has a big table of information. I don't know where it disappeared to. Yeah, so the validation component. We have information out there on evacuation orders, when and where they're being issued. Typically, that information is broken down by evacuation zones, as you know, and sometimes counties. Similarly, with evacuation rates, there are surveys after the fact that provide some information on the timing and spatial distribution of evacuation rates. Often those surveys, and like with Irma, there was 5 or 6 of them, and they broke down their evacuation rates by different spatial areas. So you had some that were broken down by regions, you had some that were broken down by zip codes, that sort of a thing. And so it was difficult to find a real easy way to combine a lot of that information together. So what we ended up doing was just kind of looking at all of it and generally saying, okay, we have high rates of evacuation here, less rates of evacuation here, and we tried to translate that over onto our 10x4 agent-based modeling grid in a subjective way. So to answer your question, it was a very subjective process, but we were just doing our best to get, I think it's safe to say that we have a pretty good ballpark estimation of knowing that our evacuation rates are highest in certain areas and less high in others. It's subjective.
Yeah, I think this is such a promising modeling framework for trying to piece together all of these different pieces. One thing I'm curious about, though, is that you really do need sort of empirical data to model these sorts of things. And I wonder, especially like in the human system, I'm curious where you think sort of the gaps are there, because I think there's a lot that we know about how people receive information, about what they do with that information that is maybe not as empirical in nature. So I'm wondering what type of work you think needs to happen in order for some of those sorts of findings to make it into a model like this. Or maybe they already are, I'm not sure.
That is an excellent question. I suspect you might have a better idea than I. But yeah, it's, our approach to this was, can we find the most important inputs and factors while also finding some, or also simulating the distribution and the complexities in such a way that at least captures that sort of stuff. So, we just made things very stochastic and random to kind of, at a high level, indirectly simulate some of the complexities involved there. But yeah, I don't know. That's a good question. We should chat more.
Thanks, Austin. I really enjoyed that. So my question is about the nonlinearity. And can you quantify the nonlinearity in this system, perhaps by running quasi-linear experiments or linearizing pieces of the interactions? In other words, eliminating certain feedbacks and just kind of getting a sense for how nonlinear this system really is. Because it's not 100% obvious that you'd get a totally different answer for just a bunch of random stochastic elements making their own decisions.
I think that's a good point. And to clarify, you're talking about maybe running some simulations with the nonlinear piece blacked out and then comparing it with the simulation as it is with the yeah.
And doing it with many different, because it probably enters many ways.
Yeah, I think that's a great idea. Yeah. My intuition on it is that the traffic piece is the big nonlinearity involved there. Yeah, I think it's a great idea. Thank you.
Hey, Austin, that was an awesome talk. Thank you so much. One of my questions is on kind of the guts of how you create these agents. So each one of them individually has their socioeconomic status, their access to everything. How do you assign those? Are you just randomly pulling from distributions and then spitting it into each one X amount of times for the population, or is it a little bit more comprehensive than that, or can you describe that a little bit, please?
Yeah, that's another great question, and very similar to Andrea's, because we have data, census data typically broken down by census tracts or zip codes for these household characteristics of average age and mobile home ownership and other factors just like that, income. There's no real obvious simple way to translate that data onto this 10x4 agent-based modeling grid. So a lot of that process was just kind of subjective and looking at my model, spatial distribution, and their data and being like, yeah, that should go here and that should go here. And so it's a good question.
Okay, we are out of time officially. Thanks again, Austin. And please join us for cookies and coffee. Further discussion.